I'm excited to introduce to you Jeremy Carroll from Pinterest, which is a site that handles its fair share of internet traffic. Jeremy was the first site reliability engineer hired full-time for Pinterest, and so he's got a lot of great experience dealing with all those darn internet users. So let's give it up for Jerry.
Cool. Good afternoon. You guys having a good time at HashiCorp?
Yes, great time.
All right, good. Hopefully lunch didn't take everyone's energy level down, so try to keep this easy. So introducing myself, so I am Jeremy Carroll, and I work on site reliability engineering at Pinterest. I primarily work as an embedded SRE for infrastructure, and today I want to talk to you about Packer at Pinterest and how we use it to author machine images for the cloud. Giving you a little bit of an overview of the agenda, it's going to be done in three main parts. The first part, we'll talk about machine images and what that comprises. In the second part, we'll talk about the build system, in which Packer is a really important concept to build and author the machine images. And third, we'll talk about managing the machine images once they've actually been created. As a little bit word of caution, a lot of this presentation has to do with cloud concepts, and specifically the Amazon cloud. So you can take a lot of these ideas and boil them for other providers, as just a fair warning. So a little bit about Pinterest. So Pinterest is a relatively large site. So anything that we build or architect has to work for quite a large scale initially when it's developed and designed. The latest public statistic that we state is that we have 50 billion plus pins categorized by people into more than 1 billion boards. And if you look at the image in the background, this is a picture of my home feed currently. And the home feed is something you see when you first log into Pinterest. So Pinterest is a visual bookmarking tool that allows you to go and grab the best of the web and save those ideas into a collection called boards, and hopefully do those things later in real life. An example, a lot of things that I'm painting right now have to do with Halloween yard haunts. I'm doing like a haunted house for my kids, and you see a lot of that. There's a lot of board game stuff. I've been a member of Board Game Geek for a while. A lot of tech. I think Zelda's in the right-hand corner. In general, we're, as I said before, 100% Amazon Web Services for all of our needs to scale the site as it's growing. Before I talk too much about the actual concept of creating these machine images, there's some terminology that will make it easier to do the rest of the talk. I didn't come up with these terms. Actually, I searched Google to figure out what was their earliest reference of some of these things. And I found that there was a talk from Boxgrinder in like 2011 that coined these terms. That was the earliest reference that I could. But in general, there's a concept when you create machine images of bake versus fry. How many of you have actually heard the concepts of bake versus fry? So some, okay. So really what it comes down to is the terminology of baking and frying is how you would manage your machine images when you create them. Baking is making a purpose-built virtual machine with all the requisite software to fulfill a specific task. I like to kind of call these virtual appliances. What it means is as soon as you author that machine artifact, you press play, it does everything that it's told to do. An example, if you go into the AWS marketplace, you can find a lot of public cloud images that do this. You just press start, you get yourself a WordPress machine. You press start, you go get yourself a Docker image with something. On the other side, frying is more of a technique that is primarily more predominantly based on the cloud. So you produce a reusable machine image and then retrieve, install, and apply essential components or configuration at runtime. With the advent of configuration management tools, whatever one yours is, if it's Ansible, Chef, Puppet, or any of the other ones out there, this is more of a popular idea. You manage fewer machine images, and then you use tools like configuration management when you boot them to turn them into what they should be. And really, if you look online, you see a lot of people debating bake versus fry as a versus thing. So I'm going to do this or that. And what I'd like to tell you is that usually, in my experience talking to many different companies and ourselves included, is that people don't do this or that, they do this and that. So I kind of like to paraphrase when I talk about this at Pinterest as more of a sliding scale. So it's not you do it all or none, it's varying degrees of what type of state that you want to put inside your machine image. So for example, frying, you have less state, but you have more runtime dependencies. So I put some contrived examples at the bottom, so OS config, packages, application code, vice versa. You can really put whatever you want on that scale, but in general, it's just a framework to kind of describe what has more state and less state inside of a machine image. So one of the pros of this is that it's very reusable. You can have a very small number of machine images that can do a lot of things because they're very reusable. On the other hand, you have slower boot times because you have more dependencies to install or to retrieve at launch. If you look at the opposite side of that, if you look at baking, baking has more state, so it's more purpose-built. Therefore, it has less dependencies. But it's not very reusable. So if you're actually baking a lot of things, you're going to have more of those images because, of course, they're purpose-built. One of the pros of that is that you have faster boot times because it doesn't have to contact or install or configure any of these things at runtime. And at Pinterest, when we started looking at redoing our image creation and build system a couple of years ago, we started looking more at the baking approach, mainly because autoscaling was a primary driver of the system. So those who are not aware, autoscaling is a construct, specifically at Amazon and other cloud providers, where you can scale up your platform depending on load or demand. So some of the properties of having a reliable, reproducible, known boot time was very attractive. Which leads me to one other point about SLA inversion. If you've ever read the book Release It from Michael Nygaard, he has a really good chapter about SLA inversion. But the basic premise is that the availability of your service, and I'm using the machine image building process in this example, is dependent on the services you depend on to actually do that task. So in the fry-based model, you might have a lot of dependencies. Now I put some other examples up here. So for example, if you're frying, putting less state in an image and doing more at runtime, the availability of that launch process will be primarily driven by the availability of all your dependencies. So example, if you have a Python repository which has 3 nines of availability, you require DNS, maybe an apt repository, maybe DynamoDB or Puppet, the availability of those systems are going to affect your ability to launch that instance. And at Pinterest, when, the first system, we primarily did fry-based for everything with Puppet as a configuration management tool. So when we had large-scale events and we had to bring a lot of instances into production, we had thundering herd issues with apt repositories. Or maybe we did not cache a public repository and they were down. Maybe the Ruby gems is down or some other type of repository was down. So that affected our ability to auto-scale quickly and reliably. Also, the not knowing the boot times, because all these systems are kind of variable based on load, kind of led us more towards the baking approach over time for auto-scaling services. So as an overview, just want to do the kind of the key point. In my opinion, the bake versus fry debate, bake versus fry, is kind of moot. Most people do both. And in general, baking increases your reliability of the system by removing and decoupling yourself from lower availability services. So if you want the highest levels of availability, you can bake more of that and take it away as a potential dependency or a liability at runtime. So coming into the build system. So when we started creating this build system, we kind of looked at it from the requirements first. We wanted a reliable, repeatable, testable build infrastructure for the cloud. A lot of the previous system, which I'll go and explain in a couple of slides, was based on technologies that didn't have these type of properties. And the reason why auto-scaling was important is because this is some ideas of the things that I'm saving to a board, and we wanted to make sure that we could scale to meet the demand that Pinterest was available so people can be inspired about the things they love. So a little bit, this is very Amazon specific, but it kind of just gives you an idea of actually machine image and machine image building. I took this directly from the Amazon website, I think last night, so it's pretty relatively current. In the upper left, you kind of see the AMI lifecycle, or machine image lifecycle. It's how a machine is born and destroyed. And then in the upper right and bottom right, you'll see the different types of workflows it is based on the type of machine image it is. So at Pinterest, we use both elastic block stores for root volumes, which has state that can survive reboots. We also use instance stores because we use some instance types, mainly solid state ones, that do not offer those as root volumes. So because of that, they have different flows through the system. The general purpose is that you first have to create your machine image, register it, and then from there you can launch an instance into production, or you can copy it to create a new instance, or they'll destroy it by deregistering it. The important part to realize through this flow is that machine images have ancestry. You can build a machine image from a machine image. And that's the key point. And how you build this It has a lot of little details and little idiosyncrasies which make it relatively difficult to do without a lot of reading. Coming into image states, so I said before that images can create other images. So with this, when you're baking images for the cloud, you don't want to do everything from the ground up every time you want to build an image, mainly for provisioning time. So an example is that I don't know if any of you used Gen2 a while ago, but if you wanted to emerge a stage 0 or build the entire thing from the ground up, you could. Just take you a very long period of time. So most people don't choose to compile the kernel, every binary, everything from source. They want it pre-built for them, and then they'll build off of that. The same thing happens for machine images. So at layer 0, or the foundation, there's a bare bone operating system, a very minimal installation. And we use the same terminology other people in the industry like Netflix do, foundation, a base application, a base AMI, and application AMI. So the foundation is basically almost nothing more than a 1404. We use Ubuntu, so like a 1404 or 1204 base image. And then the real magic for your business happens at the base image. So that's where you kind of create your platform operating system with your best practices. An example is these are the things that we'll share across every image that you build after the fact. So we use Puppet as configuration management, so we'll install Puppet across all the infrastructure. All the security best practices that we'll do inside the base image. But the key point is that everything in the base image is reusable across any other application image. And then the third, if you go more towards the baking state versus the frying state, you'll have an application-specific image, which has more things like maybe their specific tuning, the code or configs, or any other type of packaging. The one thing about the system is since you build off of the previous layers, is that there's a side effect that anything that you need to rebuild from a lower layer actually regresses through the upper layers. So for example, if you have to fix something at the base AMI, then anything built off of that base AMI will also have to be updated. So also the lower you go down, like foundation and base, you rebuild those less frequently. So there's not as much turn for that. So some of the side effect is mitigated, at least that. So it wouldn't be fair to talk about our current system until we talked about the old system. And I don't think this was too uncommon in the industry before tools like Packer were born, is that we had a bash-based build system that we took for some really great community resources. The one that we used at Pinterest for a while was based off of Eric Hammond's stuff. He put some bash resources out there to build basically foundation AMIs and base AMIs. And at that time, we fried everything. So we had one base AMI that was almost like a golden image, one image to rule them all. And then we used configuration management tools, such as we use Puppet, to then make those into all the applications that we wanted from that one base image. So the bash system, and I did put a little bit of the scripts out there, but it's very fragile. So we use chroots to actually mount the images as loopbacks and then format them and get them ready to go. At the time, it only handled instance store based systems. So EBS root volumes and Amazon started becoming more popular, and the scripts couldn't handle that. In addition to that, the bash is fragile. The error code and error handling, especially when you use pipes and pipe status, it's relatively hard to have a repeatable process with that bash system. So with autoscaling, we wanted to remove our dependencies on all these, decouple all this middleware, all this dependencies from our build process, put more of that state inside the image, but we didn't want to do this with bash infrastructure. So we started looking at Packer as an early adopter when we started redoing the system a couple of years ago. So in a general nutshell, this is kind of what the system looks today. It hasn't changed too much over time, just little tiny things. But the nice property is all of this automation was built with open source tooling. So there's nothing novel or proprietary about these components. It's just basically how we wire them together. So anybody can actually build this type of infrastructure. The components of this system are Jenkins as a build manager and an orchestration tool. It's a thing that actually manages all the workflows, kicks off all the jobs, and invokes all the components. The next is kind of like the center of the universe in this thing, which is Packer, which does a really great job on telling it from that single source configuration how to build an actual application Amazon machine artifact for the cloud. Next, we wanted testing as a core part of the system. So we actually have ServerSpec, and that's what we use today to do most of our testing. The nice thing about ServerSpec, it was built more towards server testing, and we still do other layers of testing, of course, at the config management level or vice versa, but we wanted something to make sure that all these machine artifacts that we're generating, that we do so in a way that we can have more confidence inside of them. Next, we needed something that does runtime initialization. So there's some things that can't be built into the AMI in certain cases. And I'll explain more about that later, but we needed a system that does runtime mutation of the actual instances as they boot. And we use Cloud Init for that, and we've written custom Python scripts and code to do that as well. The next is we needed a machine or image registry for machine images so we can find them, so we can update them, and we can use them. Now, internally, we use our own based machine registry, but for this talk, I don't want to talk about proprietary internal tools. So I'll talk about there's open source tools such as EDA from Netflix that will do kind of a CMDB for the cloud. And I'll give some examples how you can actually use EC2 as a lightweight CMDB if you're just getting started. And then next, we don't want to build all of these things by hand. We want configuration management to be an important part of the system. So we use Puppet as a way to reliably, repeatably, deterministically build all of this infrastructure. So Jenkins. So as an engineer, you usually don't have to deal with the Packer system or the image build system too much. The main thing that happens is when somebody checks in code, that will be hooked into the image pipeline system, and it will create them an artifact. If they don't want to do that, if they don't want to do a continuous integration or continuous delivery type system, they can go to Jenkins as the user interface. And what Jenkins does for us is it provides us that UI, because as engineers, I create terrible UIs, and I think most people out there probably is the same way. But it allows us a place for people to create new image artifacts and copy existing job workflows and set up new things to build new artifacts with relatively ease of use. The next thing that Jenkins will do is that it has testing and outputs for all the tests from all the dependent jobs as really ingrained in the product. So one Jenkins job can trigger another Jenkins job and you get all that output back. And it does a really good job at looking at all that system. And if you look at the kind of thing that build executors, it can do a lot of concurrency in the system. So with relatively few resources, we can build a lot of stuff at one time. So the way we generally set up the Jenkins workflow is that we kind of have 3 stages of jobs inside of Jenkins. So the Packer build system is really just one job artifact, and then everything else has their environment variables for configs that executes that job as input. So for example, if I have a machine image for a base for 1204, I'll just set a bunch of parameters inside that Jenkins job as environment variables, and then it will trigger the downstream Packer job when you hit build or for CI or vice versa. So basically inject that into Packer at runtime. Then Packer will go ahead and do all that stuff, create the machine image, and then when it's done with that, the machine image has passed some local tests, but maybe it's not been validated. So it can also trigger another downstream job to then launch that newly formed AMI to do another round of testing. But the general purpose is that Jenkins will manage that workflow for us. And some of the inputs we'll do, for example, is what's the test you want to run on the system. So you can write your own ServerSpec tests, or run it on that instance type. Another one is what region do you want to build this image for? What's the ancestry image you want to use? So for example, do I want to build a 1404 image with a 319 kernel? Do I want to build a 1204 image or vice versa? It's up to you, it's based on environment variables. And the next is like a Puppet role or module or class so that our masterless Puppet system can pull in the right dependencies and then build on that system. Other things, there's many other options, don't want to go through all of them, but it's things like instance type or vice versa. The important thing is that we're going to put a link to some examples on GitHub at the end of this to not show too much code on here. But one of the things that we had to do with the RSpec framework is use the, I can't pronounce it, but it stands for Yet Another JUnit RSpec framework. But basically what we'll do is output all the ServerSpec job runs as JUnit test output so that Jenkins can read that and show that unit test in the direct jobs. So you can go to Jenkins and see, yep, here's all the umpteen million tests that I ran for all these images, and here's the pass status and whatnot. So as I said in one of the original slides, is that images create images. So they have that ancestry model. So the way the build process works is that, for example, if I want to create a base AMI, you'll go ahead and find the foundation AMI. And we don't want to hard code any of the image IDs throughout this entire process, because that kind of defeats the point of having a dynamic build system. So what instead is that we'll query the image registry and we'll say, based on my requirements as user input, like the version, operating system, kernel, vice versa, find the foundation image that I want to build from. Next, the Jenkins job will take those all as environment variables and tests and then render a packer.json template. Then Packer will read that template and then go ahead and create that machine image artifact. While it's building that, it'll do some rounds of ServerSpec testing based on the Puppet integration test, which I'll cover a little bit, which creates an AMI machine image artifact. That also updates the image registry so that it can feed into the next system. So that means that if I want to create an application AMI, then I can just use the same system, same build system, just change the parameters and say, now I want to build off of this base AMI. So now it's the base AMI for 1404, kernel 3.19, and it'll go through the exact same flow. So in general, the Jenkins workflow is very reusable. It's basically just a meta template on how to build the system. So essentially we're at HashiCorp talking really about Packer. It's a really great tool. If everyone here is aware, if you're not using it, it can basically read a JSON file, which has a lot of different options. It's platform agnostic. So when we're looking at this, we looked at other open source projects at the time, and they were some of them were very opinionated. They were opinionated for certain cloud providers or certain parameters or ways or workflows of building images. And at the time, Pinterest was primarily instance store driven for its machine artifacts, and a lot of the open source tooling we found only worked with EBS. So it's kind of nice to actually find Packer, which had really high degrees of concurrency being a Go framework, replaced all that hard to build bash infrastructure, and then also was platform agnostic. So in the future, if we want to try to build any other type of images, such as even Docker containers, we can use the same system to actually produce those artifacts. In addition to that, since the way Packer works is that it usually launches the machines inside of EC2 to actually perform the baking process itself, it doesn't take a lot of infrastructure for us to have high degrees of parallelism. It's not uncommon for us to have one Jenkins slave with 32 builders that can actually just do that many machine images at once. So it does. So some of the other systems didn't have a lot of good concurrency. It would take a lot of Jenkins masters or build systems to do the exact same type of thing. But the important thing to realize about Packer is that, in my opinion, it's a great tool, but it's not really a tool that you want your engineers to directly interact with, mainly because it's JSON. Engineers don't do a really good job reading and parsing JSON. Also, the size of the JSON templates that we render are relatively large. The amount of provisioners, builders, all the things that we do in Jenkins, it can get quite lengthy. So it's hard for people to kind of grok. So one of the things that we did was we created basically some Python code to build the Packer JSON file. So again, given the parameters, this code can then read the environment variables, go find that ancestor image that you want based on your query pattern, then go ahead and render the template based on what you are. So you pick the right provisioners, it can actually put the right environment variables in and whatnot. So our engineers is pretty easy. It's just give me the most recent tested version of the base image and go for it. And then merge it all down to that, and then it can then just execute that and go. And the reason why that's important is because I committing a cardinal sin here of actually putting code, especially a lot of JSON code on the whiteboard. I'm not expecting everybody to read this. But in general, engineers don't want to go ahead and write some stuff like this. The nice thing, though, about Packer is that it has really good support, first-class support for environment variables. And since Jenkins is very environment variable driven, we can actually use that to drive most of the things inside this manifest. The key thing that we wanted to kind of put inside here for me to show this was just having standards. So having naming conventions and naming standards for your images. And this is just an example of how we did some of our naming, and there'll be other examples afterwards. But it's nice because when you want to go manage these images after the fact, to have that there. So for example, we have application as part of the AMI name, the version, the architecture, when it was built, the type it is, if it's an EBS SSD, if it's an instance store, or vice versa. And then we put a lot of other description or metadata on that artifact, and we upload it to the path in S3 for an instance store or vice versa, or put the name of the AMI as EBS that matches the same thing. So we can find it relatively easily after the fact. So in testing, ServerSpec is really nice. The basic way to describe it, you can go to serverspec.org to actually figure out all the syntax and whatnot, but it's a Ruby RSpec framework to test servers. So as I alluded to before, we have JUnit output, and the way that we work is that when we build the image and put in the Puppet role, and then our Puppet infrastructure will converge and create that, we run the Puppet test as integration tests. So we want to make sure that all the Puppet modules, all of them get together correctly and merge correctly on disk. And that will test, and I gave you some artificial examples here for, let's say you don't want to bake keys into your instance. So we're like, well, part of the cleanup process, we shouldn't be baking our credentials in the instance. We shouldn't have the apt policy that stops services from starting. We should make sure that's removed before we bake the instance. Or other things like make sure the time zone's set correctly. Now, at Pinterest, we have hundreds of these things, so it all depends on the size of your testing infrastructure, that how many of these runs, but ServerSpec is very fast. Running these tests actually only takes a matter of seconds. Most of the actual time in the build process, which I'll cover a little bit later, is outside of the actual testing framework. So as long as you have the environment to this, you pretty much get testing for almost no additional time. The other thing that some people can choose to do, depending on if they want to, is acceptance tests. So example, once we create that AMI, then you can launch it and then do actual acceptance tests. So rather than everything looks correctly on disk, we'll say, actually, I'm going to try to query LDAP, make sure I get results back. All those type of things to make sure we're actually doing that. The reason why we put that as a core concept is that, if remember, when you rebuild the image layers lower, you have to rebuild everything above it. So having regressions in a base application AMI is a relatively expensive thing to fix. You have to go find downstream, you have to rebuild all those packages. So we'd rather take additional time when we create the lower layer images and test them a little bit more, more thoroughly and take that time, because the time to go and undo that and get it right is a lot longer. So it's well spent. So the next thing about CloudInit, this is an important part. So some things we cannot bake into the image. So we use a lot of instance store volumes for databases and SSD systems. And in that case, if it's ephemeral volumes, like the ephemeral volumes it gives you, we can't handle that at runtime. Bake that in. So if, for example, we want to format the disks, so we want to format them based on the application owner's requirements. So we JBOD them, RAID 0 them, have an XFS file system, the different stripe sizes, stripes widths. All that stuff has to happen at boot time for a lot of these instances. Then they'll update an etc. FS tab, so it's reboot safe, and we're good to go. Other examples, and there's more, is, for example, setting host names. So one thing that we do to encourage people treating instances as cattle, not pets, is we use UIDs for our host names, but we still have to generate those and save them. Key credential management for the initial boot. So EC2 will actually do key rotation or vice versa. Another option that we have is that this is more of a framework for people to work in. So there's an option to run a Delta run in Puppet. So one thing is that, as I alluded to before on bake versus fry, when you bake an instance, it doesn't mean that you can't fry it again at runtime. So this is one option that we can offer some people. So they can actually treat the baking infrastructure more as a cache for configuration management, and just add the additional dependencies that they actually have in their Puppet manifest for their modules. The nice thing about that is that if some people have high velocity, they can choose to use that. Then at boot time, they'll run a Delta build, which should relatively be quick with masterless Puppet, and then do that on the fly. And that's optional depending on what people want to do. Another thing is, for example, updating DNS and Route 53. I can only do that once I generated a host name. So there's many other examples. The nice thing about CloudInit as a framework is that it's a Python-based system. It has a lot of conventions in there that you can say, run this only once when the instance was first initialized, and it will do it one time. So for example, you don't want to re-RAID your disks if you reboot. Another example that they'll have is that you want to do this every time you boot. So you can have your own post hooks, pre-hooks, all that stuff inside the build process. And at Pinterest, we have engineers that worked on the ordering of this stuff so that we can halt the OS builds until some of these things happen. So you can actually have some control over the ordering at runtime. One thing about configuration management systems, and I want to kind of call this out here, Puppet is just one example, is that if you're using this to kind of converge and create your images, some of these dynamic fact-based stuff actually becomes an anti-pattern that you have to be aware of. An example is that if you want to bake the whole thing and you're not going to run Puppet at boot to do a Delta, you're going to have it all immutable as much as possible, then if your Puppet convergence has a fact like hostname or domain, then you're going to bake the config as the machine that actually baked it. So it's going to be false at runtime because it's going to be a different machine. Maybe it's going to be in a different availability zone. And one example that we've actually seen is people putting cron entries with random numbers. So they want to go ahead and say, all right, I'm going to random splay this 0 through 1 hour or vice versa. Well, if they bake that in, then that means every time they auto-scale their system, because that's what they wanted to, everyone's going to run their cron at the exact same time. So there's a kind of caveat emptor that certain things, even though you have to be wary if you're actually going to bake this state inside the system. So some of these things you could move to cloud init to do, or vice versa, or mitigate by not doing it, but you just have to be wary that some of these dynamic fact-driven stuff could be dangerous. I would be remiss if I was going to describe the system and not talk about build times, because that's really what people want to know about the system. And one thing I'll put in here is I wouldn't put too much faith in the numbers that I show. It's more about the ordering and stack ranking, because there's a lot of things that can happen between the variables, the build system. But in general, what we kind of seen is that if you're making an instance store volume, there's kind of a cache layer on top of S3. If you're not aware, when you build an Amazon instance store, it has there's a 10 gigabyte root volume size limit. So you can only put 10 gigabytes worth of stuff inside the instance store itself. And when you upload it to S3, the maximum size of the S3 file, I think, is like 5 gigabytes, so it has to chunk it into small parts. So a lot of the upload time and build and bake time for an instance store volume is chunking that image, writing it out to disk, and then taking that image from disk and then putting it into S3. So that's the reason why the Amazon instance build time is one of the slowest. The faster one is more of the EBS stuff, because it doesn't actually have to do this, chunking and writing to disk and uploading to S3. And ultimately, it will just use snapshots, so it only has to copy the difference between this snapshot and the other one. The also benefit of EBS is that there is a 10 gigabyte limit in instance stores on that size, and that can't be changed. But with EBS, you can have much, much larger volume sizes. So if your customers, your engineers at your company really want to use some of the system, you have to make sure that their entire artifact fits underneath 10 gigabytes, which may be difficult depending on your type of requirements. So for that, we try to move people more towards the EBS route as much as possible for faster provisioning times and faster boot times. One thing about Amazon Instance is that the first time you launch that new AMI that you just created that's custom to your business and availability zone, the first boot will take longer. There's some type of caching infrastructure on EC2 that when you launch it, it just takes longer to copy that image down to boot. So as you go through those testing stages, it just takes longer. So the chroot stuff, that's the fastest, and that's an advanced builder and packer, and there's a lot of documentation about it. The only downside of that is that your Jenkins build infrastructure has to have executors with the certain operating systems that match what you want to build, and then you have to pin your builds to those systems. So in the Jenkins workflow, we can say, here's a 1404 on this kernel version, and it has to be running all the time to build that chroot stuff, and we have to make sure we build it on the same like system. But it's one of the fastest boot times out there. So if people really want to take a look at this for how quickly can I do a change, most likely you want to go up the stack. And finally, to the third part of the talk, talking about the image registry. So now we have a Jenkins build system that can build these artifacts. Packer's going to make it happen. We have testing with ServerSpec, and we create all these artifacts. And if the system starts getting popular, you'll realize that you end up with a lot of images very, very quickly, and you have to manage them. So example, if you use continuous integration and deployment, every code commit is going to create an image. That can be really expensive and costly and time-consuming to find this stuff, so you have to have ways to manage this metadata. So at Pinterest, we kind of built an internal simple Flask tool that interfaces with our CMDB for this type of information. What the most important part is the type of metadata that you put inside there so that application owners and engineers can know how to find their images. So for example, what's your versioning strategy? You just got to make sure you have a standard. We have the application name, the environment name, and very importantly, the ancestor image ID. Because then images create images, you need to be able to walk that chain to figure out the ripple effect if you need to rebuild something. In addition to that, there is a ton of attributes on the system on EC2, the virtualization type, the volume type. There's just ton of metadata that you can actually capture for the system. And for us, we kind of got some inspiration from the Ubuntu Cloud Image Locator. And we have a system that has a UI if you want to, that you can kind of search and type ahead for all your stuff, and it will go do a full text search and find all the stuff and bring it back. But the most popular use, I don't expect you to read that link at the bottom, but we have an API for the system, and that's the most important part. So in Jenkins, as people are working with the system, they can just put a curl or a RESTful call and say, go find me all this attributes based on all this metadata. And that's really what drives the Jenkins build system, is actually being able to do that. In addition, when you create all this stuff with all these images with all the state inside there, you need to have some things, especially if you're going to get adoption. One, you have to look at building an image janitor very quickly. And the next, you have to have a strategy for patch management and security. So image janitor, so as I said, we primarily had a lot of the more baking side of things for the auto-scaling system. You have to make sure if you have to clean up these things that you have rules to make sure that it doesn't accidentally deregister and delete from S3 or EBS volumes if they're referenced in a launch configuration. So if you have an auto-scaling group and you remove its AMI, it's not going to do a lot of auto-scaling after the fact. And then there's other rules like, for example, how many of the last builds do you want to keep? So how many days? And then how many of those images? Like keep the last 5. So maybe you say keep the last 5 images, and of those 5 images, keep these dates, or vice versa. And the important part is that some people will go behind you and not use your API, and they'll hard code image IDs in their systems, hopefully not. But if that's the case, you need to have a last launch date. And unfortunately, that the image register date and the launch date it's hard to find in Amazon. So you having your own system to calculate and capture that is relatively important. So I always kind of put, if you build an AMI, EC2 doesn't have a way for you to determine the date it was registered. At least put the date you registered in somewhere in the name of your AMI that you actually registered with Amazon. In addition to that, security events. So we did this system a couple of years ago, so we've gone through many, many rounds of patch management, Heartbleed, Heartstab, Heart whatever, all the OpenSSL vulnerabilities. And you have to have a way to determine your impact. So for example, what are the images that aren't patched? What package metadata do they have? Can you grab the yum or apt repository information off those images to figure out what's the patch management cycle of those machines so you can actually do CVE analysis for updates and security? So when you have this system, and I think this is not uncommon I think it's more common to any type of immutable infrastructure, Docker included, is that having ways to actually figure out what is inside this image is very important. So an example, when we went through the Heartbleed issue, we went ahead and just went to our system and said, find me every image before this date, because we know it's vulnerable. And then of those images, find me all the ones that are in use by ancestry, whatever's in launch configurations, or vice versa. And then that's my rebuild set. So go forward and rebuild all those systems from base or application, and then deregister the old ones when they're done. So you're going to need some tooling and vice versa about that. So rather than talking about that, I kind of said, initially, you could use EC2 as a registry. So if you don't have EDA installed or your own type of system, you can create, and we did this when we prototyped the system many, many years back as a prototype, your own type of very simple tracking tool with EC2 metadata. The one caveat with this is that EC2 tags, you can actually put tags on an image and tags on a resource, but there's limitations. You only allow 10 tags per instance, a limit of 255 characters, so it's very basic. In addition to that, it's a little bit slower because EC2 API can be a little bit slow. But I kind of put some code examples here that you can't read, but I have this code up on GitHub later as an example. But you can use an EC2 filter with Python or Bodo that you can use the tags to filter images. So if you want to start, you can literally say, at Packer, when I create an image, tag it this way. So tag it as test. And then when it goes through the Jenkins workflow to actually run the test against it, then if it passes successfully, then you can have Jenkins say, now mark that AMI as prod or tested. And then you can then use this query system to basically say, go find me all the images with this tag and this attributes or vice versa. And you kind of create your own very basic or simple image registry just via EC2, just via the API. So with that, in closing, kind of just a couple notes is that one of the common anticipated questions I get when we talk about this system is, as we move towards more of the container image in the container world, is this really still relevant? And my answer to that is yes. It becomes less relevant for certain aspects, but you still, if you're operating in the cloud and you do not want to use public image infrastructure, you need some way to build the public image, your image. So for example, you need something to build a container operating system or the thing that will run your container. So this is still very relevant even in that container workflow system. In addition, having the image metadata and registry as part of the system is going to be very important, because if you don't have a janitor process, you don't have a process to do any patch management or security management, this system becomes very unwieldy very quickly, especially if you get adoption and if you have CI and CD type system workloads. In addition to that, infrastructure as code. So don't build these things by hand. Have your tool of choice. We use Puppet, whatever you use to actually build these systems in a repeatable way. And then Packer is a really great tool at the center of an entire system. So by itself, it's okay, but together with all the workflow around it and all the system, it's a really powerful example. And rather than put too much code, I already did some trespassing by putting code you couldn't read on the screen. I have a GitHub repository out there if you want to kind of look at some basic tools that I put in there. I just wrote something very simple to show that you could use EC2 as an image registry, some example Packer JSON files that will do image validation with RSpec and ServerSpec, and a tool that if you want to use Ubuntu as your foundation image, then it's just a very simple tool that go out to Ubuntu's infrastructure and find Ubuntu cloud images for you. So then you can actually use that instead of building your own foundation from scratch to feed the system. You can use them as a foundation. And with that, just make sure I wrap it up. I thank you for your time. If you have any questions, I'd love to take them. Thanks. In the front.
Yes, you talked about images having ancestors.
Yes.
How do you avoid the hellacious pattern of, well, we just take a running instance, make an AMI from that, once we apply the latest updates. Then you wind up with an ancestry going back 300 images. And if you drop any one of those, you're boned.
Right, and that's the reason why you're exactly right. So the question was that if you have an ancestry model, how deep does the ancestry train go? Because if an image can beget an image and you keep building off of a delta build off of a delta build, it can get very deep very quickly. And the answer to that question for us is that we don't build application images off of application images. So in our basic 3-layer stack, we build foundation, a base AMI, and then application AMI. So when you do updates, almost always you do updates from the application, the base AMI again to your application AMI. So it mainly comes down to if you want to support that system, you could. But then again, the ancestry chain gets long, ripple effect of changes lower on have even wider impact. So having a limit to the depth that you build is actually kind of the pattern that we support.
Thank you.
Yep. Yes, question.
Because of patch management, what would you say the lifespan of those AMIs is before you have to rebuild them due to something like Harpoon or some CVE?
Mm-hmm. Good question. So the question was about patch management. So what's the average lifecycle time of these images when you actually have them? And the answer is that the application AMIs, they're real fast rev. Because if they're in a git commit check model or vice versa, they'll fly fast. They might only be good for a day, couple hours, especially if they're in continuous integration environment. We have some engineers at Pinterest that will every code commit create an AMI and then use that AMI in their own auto-scaling for an integration environment, and they'll just automatically promote that to that environment. They'll rev through a ton of AMIs in a very short period of time. The other stuff, the base and foundation AMIs, they don't change as much, but you're absolutely right. Every time security vulnerabilities come out, security patch management, like CVE Friday or vice versa comes out, you have to manage those. And the question is that the bake and fry, even though you launched a machine from a baked instance, it doesn't mean you don't manage it after the fact. So some of the things that we do is even though we still manage those artifacts, even if they're baked, but they just have a better chance, less decoupling on that middleware, and a better chance of making it when they auto-scale. But they're still managed by something after the fact. So a lot of those things is that, yes, we absolutely have to go rebuild those AMIs quite frequently due to those updates, but it isn't as impactful because we still patch manage outside the scope our current live running fleet. So it's not a simple problem. I think that a lot of people have that the life cycle of these things is relatively short. I don't think we have any AMIs over a couple weeks old. Except for the foundation ones, because those rarely change. I mean, foundations like 14.04.1, 14.04.2, or vice versa. The rest of them are relatively much more quick rev. Good question. Go, oh, over here. Sorry, lights are in my way. Yes?
You mentioned ServerSpec for checking the state of the server health. Did you do any functional testing as part of this particular workflow? And did you use ServerSpec for that, or was there another tool involved?
Sure. The question is that do you use ServerSpec for functional testing? What's the kind of role of ServerSpec in the testing environment? One thing is that the ServerSpec was a good choice because it tested the machines themselves, but from an application owner's perspective, it's not going to take you all the way. So for example, if you put your code in there or vice versa and your configs and the the general TOW that we kind of have, coming back to HashiCorp's thing this morning, is we believe that shared state belongs in a shared service. So for example, if we have things that we don't usually bake those in an instance, usually it's a service of some sort. So we have systems that do live feature flag flipping or vice versa, or live config syncing or live config properties, like fast properties, and that lives outside of the images themselves. So the application owners, when they test this stuff, it all depends on their test environment. Do they have an integration environment, a staging environment? So it's not a simple question from an application owner what that lifecycle looks like for the application testing. Most of the server specs testing is mainly for the image building itself. So who's responsible for the base artifact in this question? The application owners usually don't have a lot of insight or knowledge or change to actually the base AMI. So a lot of the SRE team or cloud engineering team will own a lot more of the functional integration and acceptance tests of the actual base artifacts that everyone's building off of. So it kind of depends, like it's not a one-stop shop for all things, but it does a pretty good job, in our case, catching a lot of those bugs early on in the build process where something changed and fundamentally we caught it before we had to rebuild all these images. An example that we had is that we had one bug that NSCD forgot to cache host or vice versa. And it's like, well, if we had that and some services go out to production, then we have to rebuild all of them. So I mean, it catches more of those things as it goes through the process. Cool. Well, if you have any other questions afterwards, I'll just be out in the lobby, but thank you for your time.